memorize, that you can kind of recall them and know how to use them. And we had ended up with, this was the last one that we did on Friday, where we had a series and we had to figure out what it converged to using one of the big five to figure out what it matched to. So what I wanted to look at today is starting off with this one as kind of like a warm-up, since it does attach to that last one that we did. I have this series, and I want you to figure out the sum of that series. So I'm telling you that it converges. Of course, if we had to find whether or not it converged, then we would have to do like the ratio test. I'm telling you it converges, so I want you to figure out what it converges to. Again, big idea. You have 5 series that are memorized. You want to figure out which one this is closest to, and then just manipulate it until you basically figure out what's being plugged in for the x. And again, I'm not going to start it. I want you to try it. But the ones you get to decide between are these 5. Looking at the big 5 series, figuring out which one is the best match for that, and then playing around with it until you find what it would converge to. So as you're looking at this, if you have trouble deciding which one it matches to, I always let factorials be my guide to start off. So like this series has no factorials in it. So if it has no factorials, like e to the x has a factorial in it, the 2 trig ones also have factorials in it. The 2 that don't have factorials are, of course, the natural log of x and 1 over 1 minus x. I then notice that this is an alternating series. So between the 2 that's left over, which one's going to be the best match for this one? The natural log of x. So when I think about the natural log of x, this is what we know. This is what is memorized. I know that the natural log of x is equal to, this is the one series that starts at 1, which I guess also could have been a clue that this is the one that you're using. And it's negative 1 to the n plus 1 over n times x minus 1 to the n. And we need to figure out how these kind of match up. So I'm kind of looking at things that are related. And again, a lot of students feel weird about this topic. They always feel like they're not doing anything, but we really are just kind of drawing some correlations. I see this is in the series we're trying to talk about. It does match up directly to that piece in the series that we know. I also see we have an over n that also matches up to one of the memorized series. What is different is I do see this x to the n. Let me actually grab a highlighter to do that. And this part that's left over is going to have to correspond with that x minus 1 to the n. Well, how can we do that? We need to just kind of think about properties of like exponents, rewriting the problem. If I want to rewrite the original problem, I might think of this as the series from negative 1 m plus 1 over n. If I have 8 to the n to the denominator, how can I think of that as just something to the nth power? 1 over 8, right? 1/8. Why am I doing that? Because I want this piece to match up with that piece. So if in the one that's given I have 1/8 to the nth, and in the one that we know we have x minus 1 to the nth, what do we now know x minus 1 has to be equal to? 1 over 8. So x is equal to what? 9/8. Well, where does that x go? That x goes in where the natural log of x is. So what can we say about that original series? What does this original series converge to? It converges to the natural log of 9/8. So again, we're using one of the memorized ones, playing around with it until we can kind of figure out what it's equal to. And again, what are we saying when it converges to? If you expanded that, it's an infinite polynomial. Not really a polynomial, there's no x in it, but it's a series with an infinite number of terms. What is the sum of that infinite series? The sum of that infinite series would be the natural log of 9/8. Yes, sir.
For these kind of series, will we always use a known series to figure out the sum?
You will always use a known series unless it is purely just a geometric one.
Okay.
So good question. Any other questions on that? All right, let's just move on to more types of problems. Here is one for us. I have for an always differentiable function of f, with f of 0 is equal to 1, its nth derivative, evaluated at x is equal to 0, is given by, and then we have this expression. And then we want to write a third degree Maclaurin polynomial for f of x. This type of problem, I chose it. It is one of the most common series FRQ questions. Or at least not questions. It's like the part A of the series question. It's the most common one that I could find looking over like the past decade. Let's make sense of it. I think these problems tend to read a lot harder than they actually are. So it says always differentiable. Why would we want to be always differentiable? Think about that table we used to create the polynomials. You just keep taking the derivative over and over again. So we do want it to be always differentiable. It gives us the initial condition. It says f of 0 is equal to 1. And this function is basically representing the nth derivatives. Like if I want to find the first derivative, plug in 1 for n. If I want to find the second derivative, plug in 2 for n. Third derivative, plug in 3 for n, etc. And we want to write the third degree Maclaurin polynomial for f of x. Since this is a Maclaurin polynomial, where do we know this would have to be centered at besides it's telling us? 0, which it tells you evaluate at 0. So it is centered at 0. How would you go about creating a third degree Maclaurin polynomial? Well, how do we create any polynomial when we don't have one of those big 5? We just think about that table. So I have n, I have the nth derivative, I have the nth derivative evaluated at the center, and then I have the terms, the nth derivative at 0 over n factorial x to the n. If I need to write a third degree Maclaurin polynomial, how far up do I need to go for my n? 3 degrees, so I just need to go to the third, not overthinking it. So 0, 1, 2, third degree. Do we need to spend time finding each of the derivatives as you go down? Not quite. So like this first one is going to be like the original function, and then we know we have like the first derivative, the second derivative, and the third derivative. We do want to evaluate it at 0. Well, we do know what f of 0 is. That was given to us. What was f of 0? 1. And again, that's coming from the initial condition. The remainder of them are going to come from that formula that we have. So if I wanted to find the first derivative at 0, using that formula, I'll have -1 to the first, 1 plus 1, 2 factorial. I'm going to fix my handwriting. -1 to the first, 1 plus 1, we have 2 factorial all over 2. What is that going to simplify to? We have -1, basically just -1, right? The 2 came from because I can't plug in things correctly. Try again. N is 1. Simplifying that, -1, 2 times 1 over 1. There we go. Negative. And then it really does just become more of a tedious problem. How are we going to use those things? Is we're going to use that to kind of create the terms. So for example, what is that first term going to be? Probably just based on my table, but I have the function at 0 divided by 0 factorial, x to the 0th power, which is 1. There's my first term. What is my second term? -2 over 1 factorial, x to the first, or -2x. It's asking for a third degree polynomial, so I just need to repeat that for the second derivative and then the third. And it really is just more of like plug and chug at this point. What is the second derivative at 0? -1 squared, 3 factorial over 2. So that's going to be 3 times 2 times 1 over 2, which is just 3. What is the term going to be? 3 over 2 factorial, x squared, or 3/2 x squared, Almost there. What is the third derivative at 0? Negative 1 cubed, 4 factorial, over 3. Negative 1 times 4 times 3 times 2 times 1, over 3. That numerator is going to be negative 8 over 3 factorial x cubed. Simplifying it, negative 8, 3 times 2 times 1, x cubed. 2 goes into 8 4 times, negative 4/3 x cubed. So that problem really does veer on like, hey, really more tedious than anything. The knowledge we're pulling from this is we know how to create Maclaurin polynomials. Big idea, we know how to create the terms of a polynomial. So then what is my third degree polynomial? My p sub 3 is equal to, I have 1 minus 2x plus 3/2 of x squared minus 4/3 of x cubed. Questions on that? Let's see what else we can know when kind of applying these. Next one I want to do example 1b. Same nth derivative formula, but again, let's kind of make sense of what it's asking. For an always differentiable function f, same initial condition, we have the nth derivative formula. Find the coefficient of the x to the 20th term of the Maclaurin series. So again, if I'm thinking about my table, it's not asking us to do a full polynomial, but I know we have like the n, we have the nth derivative, I have the nth derivative at 0, and then we have like our general terms. If I'm trying to find the coefficient of the x to the 20th term, well, what are we going to use for our n? 20. So again, don't worry about doing 0 through 19. Just go ahead and stop at the 20th. That's going to be the 20th derivative of x. Well, how can I find the 20th derivative of x? They gave me a formula. Plugging in 0, negative 1 to the 20th, 21 factorial over 20, and then plug that into the term formula. So again, kind of everything always goes back to that term formula. That is going to simplify and just be 21 factorial over 20. So in the term formula, 21 factorial over 20 divided by n was 20, and that's x to the 20th power. Do always want to make sure we answer the question. Sometimes the AP exam will ask you for the term, sometimes it will ask you for the coefficient. What is the coefficient? This would be the coefficient. And I would probably just be able to simplify it pretty quickly. So I have 21 factorial over 20 times 1 over 20 factorial. What's that going to simplify to pretty easily? 21 over 20. If it asked for the term, then of course your answer would have been 21 over 20 x to the 20. So again, like the math we are doing is not difficult. Like we literally just plugged in a number for n. What you do have to know again, really relying on us knowing this formula for the Taylor-Maclaurin kind of polynomials. So like that format, which will allow us to kind of answer these questions, make sure we can make sense of where these things are coming from. Questions on that one? All right, let's keep going and see if we can kind of make sense of that term formula. I'm going to skip to example 2b. 2a and 2b are kind of the same. Make sure you pay attention to how it's worded. So I have a function g of x is defined by the power series. So this is no longer representing the nth derivative. This is the function g of x, the infinite polynomial, the power series. And g of x is equal to that. And we want to find the fifth derivative of 3. Now think about why and like ways we approach this. Like a long way to do it is you could write out all those terms, take the derivative, first derivative, second derivative, third, fourth, fifth. Plug in 3 for x and hope you can figure out whether it converges or diverges and find the sum. Or think backwards. Where would the fifth derivative of 3 show up at if we were creating the Taylor polynomial for it. And what I mean by that, think about that table. What are the headings for that table? We have n, we have the nth derivative, we have the nth derivative evaluated at the center, and then we have the terms formed by this formula. First question to ask, it's not on here, but where do I know that this series is centered at? 3. So we know that it is centered at 3, and that comes from right here. That is important to notice because we'll find the derivative at 3, and we have x minus 3. So what is this question asking us to find? Not filling all the rows in, but it's asking me to find the 5th derivative of 3. That would be when n is equal to 5, of course. Where is that going to show up at? The 5th derivative at 3 is going to show up in the numerator of this coefficient over 5 factorial. Let me go back and replace that n with a 5 of x minus 3 to the n. Probably should be using g here instead of f, but I think we can still kind of make sense of it. Let's correspond some things like we did when we did the Big 5 series. Here's the general term. There's an x minus 3 to the n, which also showed up in the one that we're talking about. There is also an n factorial in the denominator, which also showed up to the one that we're talking about. What is left over? This 5th derivative at 3 is corresponding to the n plus 1 that we see in the numerator. So, using that information, what can you conclude that the 5th derivative at 3 has to be equal to? N plus 1. It's the same thing as n plus 1. So what are we going to say that's going to be equal to? 6, right? 5 plus 1, which is equal to 6. So again, a lot of students feel like they're not doing anything. Like, what math did we do? We literally added 5 and 1 together. But the idea is, and again, I probably should have put g there instead of f. If you know the generic form of all terms, you can kind of look at the one that was given and just like match up the parts that you're trying to find. Yes, Seth?
So in the yellow section on the one in the bottom right, can you just say n is 5? Just x minus 3 to the 5?
Oh, yeah. So like I should put, why didn't fill it in because it's ultimately not that important. But yeah, this would be like the 5th term since we are saying n is 5.
Okay.
What is important is that this numerator, reminding ourselves, the numerator of the coefficient is the nth derivative. So if I'm trying to find a derivative, I'm just looking for the numerator of the coefficient term. Let's do some more. And again, I know a lot of this stuff feels weird, but again, we're just kind of using stuff that we know. Let's look at 3a. We'll start doing some more fun stuff. So I have supposed that f of x is equal to the series negative x to the nth over 2n plus 1. 4 values of x for the series converges. And I had to say that so we could do some calculus with it. And it says write the first 3 non-zero terms and then the general term of the Maclaurin series for f prime of x. So one thing that I think happens, and I know I was guilty of this as well when I was a student, is that sometimes when you look at a problem like this, like it looks super complicated. Like we have sigmas here, it's asking us to take the derivative of it. But I think it's helpful to kind of put this in simplest terms as possible. And in simplest terms as possible, this f of x is a power series. Like that is a true statement. If I can spell power. That is a power series. What basically is a power series? A power series is an infinite polynomial. I like to remind myself of that because a polynomial is literally the easiest function to deal with in math. It has an easy derivative, it has an easy integral. So as long as you just keep telling yourself that crazy looking sigma is just a polynomial, it makes it a lot easier to deal with. So let's go ahead and just take the derivative of it. I like writing out the first few terms just so I can kind of recognize the pattern as well. It does ask me to write down the first 3 non-zero terms anyway, so I'm going to at least write down the first 3. I will say I often write down the first 4, because sometimes that first one will go to 0, so it's helpful to write down the first 4 terms. And then I'll have the general one as well. So what do I mean by writing down those terms? This is starting when n is equal to 0, n is equal to 1. I'm going to go out to 3, just in case one of those happens to go to 0, since I am taking the derivative of it. And then I will also just write the general term. So when n is equal to 0, plugging that in, anything to the 0th power is 1. 2 times 0 plus 1 is 1. Plugging in 1 now. So I have negative x to the first power. So it's going to be negative x. 2 times 1, 2 plus 1 is 3. So that would be the second term. Again, I just kind of keep repeating it, plugging in the squared. The 2 becomes x squared and positive. And then my denominator, that's going to be 4 plus 1, 5. And then I'll see that that pattern kind of repeats itself. Plugging in 3, basically the odd numbers. That's going to continue forever. And then we have this general term of negative x to the nth over 2n plus 1. And we know it's going to continue even more after that. Why do I do that? Again, I'm just reminding myself that that power series is just a polynomial. And polynomials are easy to deal with. Why are they easy to deal with? It's going to be pretty easy now to take this derivative. Let's go ahead and take the derivative. Let's do the easy part first. The derivative of 1 is going to go to what? 0. I'm not going to write it down. The derivative of the next term is going to be what? Negative 1/3. The derivative of the next term is going to be what? 2/5 of x. The derivative of the next term is going to be minus 3/7 of x squared. That's going to continue forever. That's also why I wrote down the first 4 terms. I knew that first one was going to go to 0. So I've answered the first part of the question. What's the first 3 non-zero terms? Well, there are the first 3 non-zero terms of the derivative. But now let's go ahead and take the derivative of the general term. So when we're taking the derivative, we are taking the derivative with respect to x, since this is the function f of x. So since we're taking the derivative with respect to x, you can treat n like a number. We're going to treat n like a coefficient. It's still a polynomial, so let's not make it more complicated. Let's just go ahead and do the power rule. I have negative x to the nth power. So first off, this 2n plus 1 is a coefficient, so it's going to come straight across. Let's take the derivative of negative x. N's going to come down in front. N side stays the same. What's the new exponent going to be? N minus 1. What other derivative rule I need to remember? Chain rule. What's the derivative of negative x? Negative 1. That is the general term. Like, you could leave your answer like that if there wasn't any other instructions. Probably could clean it up a bit to have a clear like coefficient part and then like the variable part. And kind of rewriting it, you would have, let's see. Actually, it's going to be pretty complicated to split up, but I'll go ahead and split it up. If I did want to simplify this, I have this n, I have this negative 1 to the n minus 1, there is an x to the n minus 1, and then that negative 1 from the chain rule. And this was all over 2n plus 1. So simplifying this general term, I see I have a 2n plus 1 in the denominator. And then multiplying things together, there's just like an n hanging out there. That's cool. Negative 1 to the first times negative 1 to the n minus 1. Same base, add the exponents. And then x is x to the n minus 1. So all 3 of those are the general solution. And again, what is that representing? This is the general term of f prime. Sometimes the question might ask you to just find the general term. Sometimes it might ask you to just find the first x number of terms. Sometimes it might ask you to do both. questions on taking the derivative of a power series? All right. If we can take the derivative, what else can we do? Take the integral, and this is where it gets fun. So, this is also where, I don't know, when it starts getting complicated, just remind yourself that this is just a polynomial. It's a really fancy polynomial, but it is just a polynomial. So I have this f of x. F of x is a power series, and we are asked to find the first three non-zero terms of the Maclaurin series for the integral from 0 to x of f of t dt. Why did I use a t here? Kind of like when we did the second fundamental theorem calculus, just so I don't confuse the x's and t's together. That t is just kind of like a dummy variable. Like I could really make this x whatever variable I wanted, and it's not going to change like the whole meaning of the problem. So I'm going to use a t there just to kind of keep my things separated. Let's talk about the integral. We know how to find an integral. This specifically is a definite integral. What will be the process of finding a definite integral? Don't overthink it. First step will be to do what? Find the antiderivative. I'm going to use a capital F for that. So we're going to find the antiderivative. And then after you find the antiderivative, what do? Plug in the top minus plugging in the bottom. I'm using capital F there again to represent the antiderivative. You know how to do that. That's nothing new. Like you've been doing integrals for a while at this point. So let's talk about finding the integral of this expression. So we have f of t, and what we're trying to find, let's just talk about the integral of f of t. This is the integral of f of t dt. So what I'm integrating is this series, negative, So I'm integrating the series. I'm using negative t here just to kind of keep my variables separated. That's 2n plus 1 dt. And I just want to talk about how we can integrate this. Now, I could do this one the same way where I list out the first three terms or whatever, and then also integrate it. Sometimes for me, for integrals, it's easier just to talk about integrating the series. We are integrating this with respect to t. So any n we see, we are going to treat like a constant. I could put the 0 and the x here right now. I kind of like doing it separately where I'll find my antiderivative and then plug in the top minus the bottom, just because there tends to be a lot of work. I don't want things to get kind of lost in the process. So let's go ahead and find that antiderivative. So the antiderivative of this, I'm going to use a capital letter f of x for it. As we find the antiderivative, so this is the integral of a series still, that 2m plus 1, that is just a number, so I'm going to go ahead and bring it across. I have this negative t. It's inside of an n. So what other rule with integration will I need to make sure I use? U sub technically is not a difficult U sub. Since that's just a negative t, what do we know is going to be tossed on the outside after I do my antiderivative? Negative 1. So let's think about it. So I have the negative t. What's the new exponent going to be? M plus 1. And then what do we do with that new exponent? We have to divide by it. So that is the antiderivative. Technically, there's like a plus c. Do I need to worry about the plus c for this one? No, because it's a definite integral. So again, this is the antiderivative. It asked us to find originally the integral from 0 to x. So what do we need to find next? We just need to find f of x minus f of 0. Well, how do we do that? Just plug in x for t minus plug in 0 for t. So plugging in x, this is the series, negative of negative x m plus 1 over this coefficient term minus the series, negative of negative 0 m plus 1 over 2m plus 1 over m plus 1. Does ask us to find the first 3 non-zero terms. I'll also talk about ways that we can kind of simplify this. When we found that antiderivative of 0, what do you notice about that second series, what it's going to be equal to? It's just 0, right? So if we're looking at this one, what's 0 raised to any power always going to be? 0. That literally is a series, 0 plus 0 plus 0 plus 0 plus 0. So we can kind of ignore this whole series because what is it going to be just equal to? 0.
N can only be a positive integer, right?
And n is a positive integer because we're starting at n is equal to 1.
Okay.
So I didn't write that on there, but it's implied that we're still starting at 1 to infinity. So what is the integral of this going to be equal to? To kind of write it out as a full statement, the integral from 0 to x of this function f of t dt is this new series that we got from the integral of negative x to the n plus 1 over 2m plus 1 times m plus 1. Could you simplify that expression if you wanted to? You could, yes, and maybe we might, just for the fun of it. That numerator, we have -1 to the n plus 1, x to the n plus 1. So simplifying it, that's -1 to the n plus 2, x to the n plus 1. So you could simplify, especially if this was a multiple choice one. Being aware of those exponent rules is kind of nice.
Would we have to combine the 2n plus 1 and the n plus 1?
You could FOIL it, but honestly on the AP exam, they would leave it factored out like that. Yes, Seth?
Where did the n plus 1 in the denominator come from again?
That n plus 1 came from the power rule for integrals. Add 1 to the exponents, divide by the new exponent.
Okay.
So again, it's just a polynomial. Like, what's the antiderivative of x squared? 1/3 x cubed. That's where it's coming from. So that's the series, and then to finish it out, we get to the tedious part. It just asks us to find the first 3 terms. This one is starting at 1. I'm going to be lazy and not simplify it, but the first 3 terms, the first one is going to be this. 2 plus 1, 3, m plus 1, 2. There's the first term. X to the second. Here is the second term. And we're starting at 1. Cool. Oh, cool. My window decided to restart because, of course, it did. There we go. That was fast. But I do need to reshare it now.
Imagine if my Surface could like.
Yeah, perks of a teacher laptop, it is slightly faster.
It's a way, usually.
And then again, the tedious part, we're just kind of plugging it in. So 4 plus 1, that's 5, and 3. And then the last term, x to the, I can't do math in my head, apparently. I lost track of what I'm doing. 4.
X to the 4.
Thanks. And then 6, 7 times 4. So again, like there's a lot of stuff going on, and I don't want you to overcomplicate this in your head. These power series, again, when you get stuck, just remind yourself they're just polynomials. So they have an easy derivative. They also have an easy integral. Like, I'll say easy in quotes, like, there's definitely a lot going on, but it's basically just going to be the power rule in a different way. Questions on that problem, though?
Have you ever thought about how insulting it is to call that just a polynomial?
It is just a polynomial, though, right? Like, yes, it's a complicated, infinitely long polynomial, but it is, at the end of the day, a polynomial.
You look at that series and you're like, you're just a polynomial, but I want to be more.
I guess, yes, Seth.
Why can't you use the general rule like for derivatives? Because 0 to x.
The general rule, what are you meaning?
I thought it was like, the general and like the common case or whatever that was.
So that is when you're taking the derivative of an integral. This is us just finding an integral. So that would be different if I said find the derivative of 0 to x. That would be the second FDC, which we normally don't see with series.
Okay.
Last one for today, I think. Got time? Yes, I got time. Skipping to example 4. I like this one because it's going to combine two skills into one. It's first going to combine using one of the Big Five series, and then it also combines taking like the derivative and integrals of a power series. So I want you to read this problem. I'll kind of talk about why we want to do it this way. But it says we know that the integral of 1 over x squared is equal to the arctangent of x. I should say probably I hope we know that that is true. We're going to use that fact to write a Maclaurin series for f of x is equal to arctangent of x. Now we actually started writing a power series for arctangent. We did it way back here. This was the example we did. And looking at this, like we only did a degree 2 one. Why would doing like more terms of a Maclaurin polynomial for arctangent be a little bit complicated?
It's really complicated. The derivative.
Its derivative is gross. Like you start having to do like the quotient rule with the chain rule, and it just gets more and more complicated. So there are other ways we know that we can write Maclaurin series. So like the first way we learned, and this is what we kind of started with on Thursday of last week, we could use like a Big Five series to easily like just plug in some substitution and rewrite it. Another way that we can do it is, of course, like the long way doing the table. But this is going to be like another shortcut for creating not only like the terms, but a rule without having to try to figure out the rule. So the thinking goes, if you're asked to find a Maclaurin series for arctangent, complicated, like its derivative gets gross pretty quickly. But we know that 1 over 1 plus x squared is related to arctangent. But we don't really know what 1 over 1 plus x squared is, but we do have a memorized series that looks close to that one. Which series looks closest to 1 over 1 plus x squared? The geometric one. So we have memorized the geometric series, which is 1 over 1 minus x. It is the geometric one, so that is the series where n is equal to 0 to infinity of just x to the n. So using stuff that we had done already, how can I make 1 over 1 minus x look like 1 over 1 plus x squared?
Square.
Not really just square the x, we're just going to do like some substitution, right? What can I replace the x with? Negative x squared. And again, why can we do that? It's just like function composition. So I have 1 minus, I'm replacing it with negative x squared. Same thing on the other side. So this is going to be n is equal to 0 to infinity of negative x squared to the n. I like simplifying things before I kind of deal with it. So we do have what we want on the left-hand side. Simplifying this other side. So I have like negative 1 to the nth x squared to the nth. So we end up with just negative 1 to the nth x to the 2n. That is a new series in itself. We know that that series converges to 1 over 1 plus x squared. I want to figure out what arctangent is. How would I turn that one on the right, on the left-hand side into arctangent? Take the integral. So again, this is just, I know you don't want me to say that, but that's just a polynomial. We can integrate both sides. What we do to one side of an equation, we just have to do it to the other side of the equation. What is the integral of 1 over 1 plus x squared? It's just arctangent of x plus c. Let's not forget that. And then let's go ahead and integrate this other side. So it is the series from 0. Negative 1 to the nth, just a coefficient. Let's find the antiderivative of x to the 2n. What's going to be the new exponent? 2n plus 1. It's still an integral. Add 1 to the exponent, divide by the new exponent. Technically plus c, since we have found an indefinite integral. What do we know about the plus c's on both sides? They cancel, they're the same. So what have we found? Arctangent of x without having to do like a long table. And in many ways, still using like one of the memorized 5. And this would be the formula you have for arctangent. Is there another way to do it? Yes, theoretically, you could make that table and try to identify the pattern. You would see that it's kind of an easy pattern to find, but that's like another way that you can do these problems. And you really can do anything. Like if I wanted to find a rule for like any of the ones I can find like an integral of or a derivative of, we can relate them back to the big 5. Yes, sir.
X has to be by itself, right?
So it is just by a good habit, because a lot of these show up on the multiple choice part of the AP exam, to have your final answer in like that clean form where you have the clear coefficient and then x raised to a power. And it's just like a good habit to write it in that form.
Okay.
Any other questions on that problem?
Yeah, why is the n not like 1 like last time where we added 1 when we integrated?
What am I looking at? Which line? Sorry.
Like for the series, n equals 0 all the way down. Like for our answer, when we integrated, why isn't it n equals 1 like last time?
The other one was n equals 1 because that was the given series. Oh, I don't know. I just completely made that up. So yeah, I guess, hey guys, I messed up. Typical me. But on that previous problem, I changed it to n is equal to 1 when it definitely should have said n was equal to 0. I don't know where I got the 1 from.
Well, because you're starting at 1 and 0 just be a non-zero term.
Yeah, well, even then, like I should have, the series should start at 0, but when you list out the first 3, you want to make sure you list out the first 3 non-zero terms.
Okay.
So yeah, thank you for that catch. Any other questions on this? All right, so that's where I'm going to go ahead and kind of conclude today's notes at. The homework that you can go ahead and get started on, so I'm hoping you've already finished homeworks 7 and 8. Hey guys, quiet please. You can go ahead and start homework 9. There are a lot of optional problems attached to homework 9. Some of you are just going to do the required ones, and that's fine. But one thing with series is like, I cannot sit up here and just do like every single type of series problem you can encounter. So there is going to be a lot of like learning you're going to have to do just by like trying out those different problems. Guaranteed on the AP exam, there's going to be kind of like a series question. Tomorrow, you know, is an asynchronous day. A lot of the juniors will be taking the ACT. If you're not taking the ACT, you're at home. I'm not assigning anything new, but just basically telling you to like continue working on this homework. The Unit 10 test is on Friday. Basically what we do on Friday is basically all of homeworks 1 through 9 and the briefcase binder. There is a lot this unit, like I don't want to downplay that fact. There is a lot this unit, everything from the series that we've done to these Taylor series, McLaurin series, and like manipulating them. So my plan for the rest of the week, I'm hoping you come to class with questions on Wednesday and Thursday, but those are also going to mainly be review days. So not tons of time left in class, but I am going to go ahead and let y'all get started on that homework. Some of that homework 9 I think is pretty straightforward, but it does follow almost directly like the notes did. So if you get stuck on a problem, the order of the problems in homework 9 are in the same order as that last kind of section of notes that we just did. Other than that though, that's basically it for series. Well, not it, there's a lot of series, but that's all that you need to know for series. But we will regroup on Wednesday to see where we're at.